Okay. Good evening, everyone. Quite a turnout so late in the evening for a seemingly boring session on, application, performance tuning, whatever. How many of you are really interested, and how many are lingering around for that, after drink today? Okay. Okay, good. I think there is something on the Partner Expo I saw in the agenda. Okay, so welcome everyone to this talk on Advanced Windows Presentation Application Performance Tuning and Analysis. We were still in the running pretty late for the longest session title at PDC, but we've been beaten to hell today. My name is Bart de Smet. I'm actually working on the WPF team as a developer in App Model. We actually own things like the application class, things like window, XBAPs, that kind of stuff. I actually brought somebody with me here who is Eric Harding. He's a performance guru.
Hi, I'm Eric. I'm a developer on the performance team on WPF. We brought an application today to show you that kind of demonstrates some various common performance issues, and we're going to kind of work through them, show you how to use the tools and things like that.
Yeah, so stories from the trenches, if you will, brought together, in one big application. But before we go there, I sort of wanted to, talk a little bit about the state of affairs we're in very briefly, and sort of, pinpoint a couple of things. And it's now like, a handful of years ago that we introduced this wonderful thing called Avalon, which is, the unification, as we all know, of all sorts of graphical user interface experiences. And the interesting thing is that, at that point, we didn't really have, the designer story with all the tools sort of lined up. But today it's reality. Today we have XAML sitting at the center of, that graphical user interface design experience, where you have the designer working on the same thing as the developer at the same time. And that's actually the thing that we are using today, in particular in the application that we're going to show. We created that one inside Microsoft in that particular streamlined fashion that we're talking about to lots and lots of people today, to use Blend for the design and to use Visual Studio for the coding part. And so, centered around this particular thing, I wanted to bring up a couple of things that lead to some kind of performance, things that you need to be aware of. So I've actually brought two buddies here. On the left, I have my designer buddy. On the right, I have my hardcore developer, still with a Visual Studio 2008 logo, because we're actually using 2008 today to show you everything you can do today. So it's actually readily applicable. And so the cool thing, in my opinion, about WPF, and like all the things I get excited about, is the fact that composition is at the center. Now, this composition thing, in this particular case, means XAML. I give something to a designer, and he can party on it. And I'm a developer, and I can also start refactoring things and, make user controls and whatever. So that compositionality allows arbitrary nesting of content, controls, styles, visuals, data templates, whatever. And that's a very powerful thing, but unfortunately, in some cases, it also brings, that tension field between those two people. I'm not going to emphasize that tension because, people like to make jokes about designers. I will try to keep it to a minimum because we need those people. I'm a developer, I can't design fancy UI. I can do a boring button in the center of a screen, that's about it. So we need those people, but we have different ways to look at the same problem. If you take a look at designers, they typically don't care that much about resource constraints. Go, for example, to some web designer. What a web designer will do with a single table that's a single element in my HTML tree, they will come up with 22 CSS style sheets and 50 nested tables to render the thing correctly. I wouldn't come up with that thing, so they have different perspectives on making things look nice. And we see lots of things there that we will actually show, like having excessive number of effects sitting everywhere that can lead to intermediate render targets, which is something we'll talk about. Sometimes they go a little overboard in using images for animations instead of using like XAML technology there or other ways to sort of visualize something. And they use what they call rich templates, but in reality it's sort of, having lots of controls that sort of get layered on top of buttons, and every single button in your application gets, kind of bombastic from the element tree. Then on the right-hand side, as a developer, we also have things to think about. And that's also something we're going to emphasize today. Things like, for example, the number of modules you're loading, the cold start and warm start time of your application. Potential memory leaks, you need to know it's not because we have a GC that it's like the silver bullet that solves all memory problems. So we'll actually show a couple of those as well. And large element count. And the large element count in the case of developers comes from different, ways of thinking about an application. With a designer, it's sometimes kind of accidental, but with developers, it's because we want to encapsulate certain pieces of functionality. We want to say, well, I have something that I want to sort of split out and reuse across my whole application. Well, in that particular case, I'm going to use a user console. So large element count can also be a problem in certain cases. So now, before we actually get into the demo, some general truths that are sort of the red thread throughout the whole presentation, things that will come back all over the place in all sorts of fields. And the first thing is something that every performance guy will tell you. You can't tell anything about your performance without measuring. And of course, measuring is one thing. If you don't know what to expect as the values in that particular measurement, you still are not doing performance analysis. So start measuring early. Do it on representative hardware. It's kind of easy today to fall in that trap because, like, as a developer, you have like quad-core machines with an SSD drive, whatever, and you won't actually see things like cold start problems, while your people actually using it might hit those particular problems. So that's an important thing to keep in mind. Secondly, my favorite thing in all the tools that we are showing is their capability to sort things descendingly. Show me the things with most memory usage. Show me the things that spend most time in the CPU. That kind of stuff is the low-hanging fruit to concentrate on. Don't start, to optimize like little things. So again, measurement is there, the thing that actually will help you drive your performance analysis. Then a third thing, and that's kind of unique to user interface design, is the fact that perceived performance is, the most important thing. It's not just wall time. In certain cases, you have to go out to the network. In certain cases, you have to wait for certain things to happen. Well, the worst thing you can do is make your application not respond, block the UI thread, whatever. So with perceived performance, it's all about making things feel fast. And it's not necessarily the case if you use your watch and actually start measuring that the thing is really fast. It's just, how things feel. And sometimes you can't actually make it much faster, so you have to make it feel right. And finally, that's with everything in computer science, of course, you will have to make trade-offs sometimes. We'll show a couple of technical trade-offs, like certain features in WPF that trade CPU versus memory and, disk access times for other things. But there might also be trade-offs, just in your project about certain features that you have, that sort of drain the performance that you need to rethink and sort of do a trade-off between the performance goals of your application and the functionality. So what we've brought today is this new application. It's a demo application from people closely related to the WPF team at Microsoft, called a group called UX Labs. And it's this thing called Fishbowl, which is a little Facebook application that sort of emphasizes, readiness for Windows 7. It's a light-up application. It's basically, you can share out status updates, browse photos, all of that kind of stuff. And we created it inside Microsoft together with like external designers. So we actually sort of use that particular paradigm that we're telling people to use in real-world application scenarios. It's built on .NET 3.5 SP1, which means that you can take a look at it today. You can actually see like the things to focus on in existing applications. We'll also talk about certain things we've done in .NET 4 to make things better. So, but it's mostly about technology that's there today. And finally, I have also a couple of links over here. They are not active yet. We're announcing Fishbowl pretty soon, so you actually get a sneak peek today. We start with the application unoptimized. We'll optimize it by the end, and that will be the thing that you will actually be able to download in a couple of days or something. Okay, so I'm actually switching heads now. Like, instead of being somebody who works on the WPF team, I become a CAD, which sounds kind of a designer, but I'm a casual application developer. I brought this application, and that's actually what Eric does quite often. He gets applications from the field and starts analyzing them. So why don't we open up the application and see how bad it actually performs?
Okay, so let's start taking a look here. I'll open the application so you guys can see it. And I'll also, usually the first thing I do is ask, what's wrong with the application? So, do you have a specific list of grievances?
Well, there are a couple of things there. Like if we looked at Process Explorer and all of that, we have quite some memory utilization. When we started the thing, you also saw like a big blankness when we were actually loading that master list view. So there are a couple of things here to take a look at. And I actually suggest that we start with the memory thing, which is kind of high.
Okay, so let's take a look at the memory here. Looks like we're hovering around 150 megabytes of memory. Now, it's a rich application. We can see we've got quite a few images and things like that, icons, things like that. But in general, I'd say 150 megabytes is higher than what I would expect for this sort of application. So Process Explorer does a great job of sort of showing us how much memory we've allocated. And what I'm going to move to next is another sysinternals tool called VMMap.
So you can get it on TechNet. It's one of the sysinternal tools.
And what this will do is break down all the memory usage, both virtual and committed, and show you where your memory is going. Now, image memory in this case, that's your EXE, your DLLs, things like that. But what we're really interested in today is the managed heap and heap memory. You can see that right here. In this case, we're actually using more native heap than managed heap. And I thought you said this was a pure WPF application.
Yeah, it's all written in C#. So like why there is like native heap, maybe it's CLR, but maybe it's a little too much.
So one potential cause for this is usually when we see large native heap. Of course, there will always be some native heap. The render thread uses native memory to hold things like this. But usually when you're seeing this number get particularly large, it's related to image use in the application. So we can browse over to the application folder real quick and just to take a look at what images we're using. So here's the project folder, and we'll just do a quick search for file name, star.png, and this sort of brings up a list of all the images in the application sorted by the dimensions. So we can scroll down, we see we've got a lot of icons, things like that, but we get into this range here, it looks like we've got quite a few images that are 294 by 272. Mm-hmm. And it looks like this might be that loading animation that we saw in the beginning.
So yeah, that's actually something that happens quite a bit in the field. You know, people create like clients for Twitter, whatever, and you know, for loading animations, they actually go out to the designer, and the designer creates like 140 images or something and hands them over. So.
Now, one thing to take away from this is while these images on disk are only about 32 kilobytes each, you say, well, you know, 30K here or there, it's not such a big deal. But it looks like we have quite a few of these. If we bring up a calculator real quick, each of them is 294 by 272. And then we have, how many of these do we have? Looks like 114 of them altogether. So if we multiply that by 114, we can see that
actually times 4, because it's 4 bytes per pixel, right?
And times 4 bytes per pixel, because they're 32-bit color. We have almost 36 megabytes of image memory just tied up in this one animation.
And so that's part of the native heap.
And that would definitely show up on the native heap. So I'm going to start another tool now. This is the SciTech Memory Profiler. This is a .NET Memory Profiler. There's quite a few options. If you're looking for a memory profiler, you may be familiar with the CLR profiler that Microsoft releases for free. This one costs a little bit. You can find it on memprofiler.com. This is the one that the WPF performance team uses internally. The way it works is you collect snapshots of your application as it's running, and then you can diff those snapshots and see how your memory changes over time. So this is a great tool for seeing where your memory is allocated, seeing how it changes over time, whether you're freeing memory and tracking down memory leaks, of course.
So one snapshot is before we start loading animation and one is after, or?
Right, so in this particular case, in the interest of time, I've pre-collected these profiles. The first snapshot, snapshot 1, starts at right after the splash screen, right after the application is initialized, and snapshot 2 is after the application has fully started and has kind of reached its idle state. So what I'm going to do is it has this great filter option. Since we know that we have quite a few bitmap images used during the startup path, we can filter down to types which have the word bitmap in their name. So here we go. We have bitmap image. If you can see that, there's 259 of these alive in the application right now. One thing to keep in mind is that when you do click snapshot, it forces a garbage collection, so you know that anything you see here is actually alive in the application. Now, since I have a difference diffing these two snapshots, it also shows me how many of these are removed since the previous snapshot. And in this case, none of these have actually been freed already, so this may constitute a memory leak. So I can double click here which takes me to this view. Now, on the left-hand side, it shows you one row per image for each image in the application. Now, one thing to keep in mind is this only says 204 bytes per image. And you have to understand the way WPF uses images, the actual bits is on the native heap. Like we mentioned, the managed objects that you manipulate are really just a pointer to that native buffer. You can see on the right-hand side, it shows you exactly where this image was allocated. And you can see the loading page is the culprit for quite a few of these images.
Mm-hmm. So you told me that we actually do a GC every time we collect snapshots. So in this particular case, the loading animation is still in memory, although we've already passed beyond that.
That's exactly right. And if you see at the bottom, we do have 114 of these bitmap images. 114 of the images alive in the application are because of this particular path. This other tab, shortest root paths, basically what this does is it shows you why these images are still alive in the application. And you can see fairly quickly that it looks like that loading page is still alive, still holding on to these images, even once the application has reached a steady state.
So essentially what it shows here is like how the GC finds out that the image is still alive, right? Those are the GC roots.
Exactly.
Okay.
So a way to fix this would be to null out this loading page and always run it again to make sure that changes that you've made have affected the application. Sometimes this is an iterative process. This shows me the shortest root path to these images, but if I null this out and I find they're still alive for some reason, you may have to null out an additional path. So sometimes it's just an iterative process of going one by one and making sure that when you think you're done with something, that it's actually gone.
Okay. So let's actually switch back briefly to the slides while Eric actually prepares the next demo and go over like the things we sort of learned here. I'm actually going backwards, which is not cool. So we've actually used a couple of tools here, which everyone should have in his toolbox, like Process Explorer is like my replacement for Task Manager. And so what we learned here is like one common cause of like leaking memory is images. And that's something that actually comes from that interaction with designers where they actually give you a whole carousel of images. Now, you will say, well, that shouldn't be a problem, but like if you're doing things like in our application where we have some static service provider where we load all of that kind of stuff and actually stick it in a static field, you can still have memory leaks there because those statics are still alive. So the way to analyze that is by using any kind of .NET memory profiler. The one we've used here is the Cytec memory profiler. And you actually watch out for allocation stacks and find the shortest root path, which actually pinpoints the most likely cause of still holding on to that particular memory. There might be multiple causes, so you might actually have to rerun the tool a couple of times. And then a thing we didn't talk about just yet, but we'll actually talk about it later on when we talk about runtime performance, is the element count. We'll see that this application has quite some elements sitting in its loading page and in its first page where it shows all of your contacts. Well, the number of elements is of course also a source of memory usage. And in particular, virtualization there with like data lists and all of that kind of controls can actually help significantly to shrink that down. But we'll actually talk about that on a separate basis. So this is actually the checklist that the perf people actually go through quite a bit when they analyze performance of real-world applications. So we started by looking at memory, but another problem that actually we saw with this application is it takes quite some time after the installation to sort of launch it the first time. And that's what we actually call cold start. So let's take a look at that as well. Okay.
So cold start, the number one thing to keep in mind with cold start is that it's all about disk I/O. So what you really want to do is absolutely minimize the amount you're reading from disk. In this case, I have instrumented Fishbowl using ETW. It's event tracing for Windows. I think that's part of the XPerf tool in particular is part of the Windows Performance Toolkit. And there's a session on Thursday morning where you can find some more information about that. Essentially what you do is you define a provider in your application and then you turn on that provider to log events very precisely during startup.
I believe there's a separate talk on ETW on Thursday. Right?
On Thursday, there's a talk you can go to. So this is what the trace looks like. It shows you very precisely how much CPU you're using per process. It shows you disk I/O information, disk utilization, process start and stop, And at the bottom, you can see events that are emitted specifically for this application. In this case, you can hover over them to get a specific name. In this case, hopefully you can read that. This is the main window constructor event that gets emitted as the main window constructor fires. So we can scroll up here. We can also see CPU time by process. We can filter this down.
You said this is part of 2010, is that right? This tool is part of...
Oh, this tool is actually in the Windows SDK. So you can actually get it there, like the Windows Vista SDK is, and the Windows 7 SDK is the latest one. And actually, there's a tool called Xperf and Xperf View that you can use for this.
So the thing to notice here is that the process is using almost no CPU time right as it starts up because it's totally bottlenecked on loading mostly disk I/O. It's loading images, loading DLLs from the disk. So the best way to improve cold startup time is to pay close attention to your disk I/O and reduce that. Having instrumented this, I can highlight the region that the profiler has indicated is my application constructor. I can duplicate this view.
So essentially what you did is like you emitted an event at the beginning of the constructor and at the end, right?
And at the end. So basically, this sort of brackets the startup time of the application. I can select this, go to the disk I/O chart, and get a detail graph. A summary table. And basically what this does is for that time period that I've selected and the time period that I've specifically emitted events in the application, so it's very precisely bracketed, this shows me which files I touched. And on the right, as I scroll over, it shows you the exact size read from that file. It shows you the number of reads to that file. So the number of reads in this case is almost, if not more important than the total file size read. Each read could incur the latency for seeking the disk out there, unless, of course, you have an SSD. So a good practice when you're looking at cold start is look at what files are read, make sure that you know why they're being read, and make sure that they're being read for a good reason. In this case, things like presentation framework, presentation core are taking the most reads. Those you'll see in any WPF application. System, of course, for any CLR application. But things like system Windows forms, and down here, system.drawing, these are DLLs that you should not necessarily see in a pure WPF application. If you're seeing them, it might be something to take a look at and figure out why you're seeing those reads. That might be able to, as you scroll over, you can get an idea that not loading system Windows forms could save you, it looks like, a little over 200 milliseconds in this particular case. Mm-hmm. So I'll switch back to the memory profile that we were using earlier. And it has this great show hierarchical feature. You can basically check this, and it will resort the list of types that are loaded by which assembly they came from. And then you can sort by the number of instances and just scroll down, and you can see DLLs and assemblies that are loaded, but only using a few types. In this case, system.drawing here has only one instantiated type. So we incurred a disk read and a seek and a DLL load for one type, in this case, the rectangle class.
And I believe the WPF has a rectangle.
It does turn out that we have a rectangle in WPF.
Just asking, you know. I don't know.
We can also look at system Windows forms and do the same sort of thing. Here we see several internal supporting types, but it looks like the main type that we're referencing is actually the screen class. So again, we're pulling in 2 whole assemblies just for this screen class. And again, we can double click on this, get the allocation stack, and we can see exactly where this was created, which is the main window constructor. It looks like a utilities class of some sort.
Yeah, so that is actually the head album class, which we actually had before Facebook, which was our prototype application. And that was actually written in WinForms. And there were quite some interesting utilities there that the developer simply copied verbatim to the WPF application. And I guess that's why we're actually loading those additional types.
So we'll switch over to Visual Studio, take a look at our main window. We use that isOnScreen method. So we can jump down to isOnScreen. It looks like we are loading the main window bounds from our settings class and just testing to see if they're on screen in case the user has changed monitors or something like that. So if we jump to the definition, we see that that's exactly what it is. We have a common utilities class that may have been pulled in from another project, and we're now incurring 300 milliseconds of cold startup time just to check if this is on screen. Now, ways to fix this If the application, if the functionality is available in WPF or in an assembly that you do need to load, use that. If it's something where you're really just calling out to Win32 to get some data, you could consider using a pinvoke rather than loading an additional DLL. In this case, we do have this functionality available, so we can just return the system parameters. Class has a...
I think you're missing some part. Yeah. Capital P.
Has a work area, which is effectively the visual area of the screen. And we can just return that contains the region. And we don't need this other function entirely. We can rebuild that. A good hint here that you're using the wrong assembly is you notice we had to cast all of our main window dimensions to integers instead of floats because we were calling into something that was not designed by WPF with WPF in mind, so you're using integers. So then if I run this, we can verify really quickly with Process Explorer again. We can see which DLLs are loading. If we scroll down, we should not see WinForms loading, and we don't. So
even though that other method is still in there, but it doesn't get called, right?
It doesn't get called, so because we're using something from an existing DLL. So with any luck, that will get loaded automatically because when you're touching other nearby functions. Another thing to do is just use something like Process Explorer to scroll down, especially if you're concerned about cold startup time. Just scroll down the list of DLLs that you're using and make sure that you know why you're using them and that you're using them for a good reason. So here I notice we're loading enterprise logging. That's a fairly heavyweight logging library for a desktop application, and we seem to be loading it in the startup path. Is that something that you intend to be using?
Well, what we actually did there is we use enterprise logging because patterns and practices told us to do. No, just because it's a nice library. But I think we've actually disabled that programmatically. So there's a setting in the config file, and if that's set to false, we won't actually go into the logging part.
So here I see it in your main window constructor. Looks like you're initializing enterprise logging. Now the thing to remember here is to know how the CLR loads types and loads assemblies. When you hit a function, whether or not an if statement will be traced, it statically determines which types that function references and loads assemblies based on that. So as soon as we hit the main window constructor, it went ahead and loaded the enterprise logging library just in case this if hit this case. So even though it's turned off, it loaded it anyway. So of course, the way to fix this is we just refactor this, extract a method, call this from a different method. And as long as this log message doesn't get called, we should expect not to see this get loaded. And we'll save that, recompile.
I think I could come up with that solution.
One thing to keep in mind when you're doing this kind of tracing is that sometimes the CLR can play tricks on you, and it will inline these functions. So when you're testing this sort of thing, at least when you're doing the final test, always run release mode without a debugger attached, and we'll verify again. We don't expect to see enterprise logging loaded, but there it is. And the reason for this is we refactored that to a separate method, but it was a very small method, and that method got inlined.
So the solution is to make it bigger, I guess.
That's one option. Another option, there's a method impl attribute that you can put on your method, which has a method impl options dot no inlining. This is basically a very explicit hint to the CLR that says, no, really, I meant this to be in a separate method for a reason. I don't want to see enterprise logging. If we rebuild and rerun, again, without the debugger, we can verify that it is actually gone. There's the build. And we'll scroll down. And no more enterprise logging.
OK, looks good. I think we can summarize off the cold start analysis here. To make sure, for cold start, of course, your machine needs to be cold. That's the first time after you install the application. In this particular case, we actually had all of those. Profiles collected up front. Am I in the wrong direction here? OK. No. I'm sorry for this. So for cold start, it's all about disk I/O. Make sure that you actually keep that in mind when you're the developer and you actually have one of those fancy SSDs, that you don't make the mistake of actually running all the tests on your machine, because people out there might actually be hurt by loading a massive amount of modules. Now, again, we've used, in this particular case, we've used Xperf to see where things get loaded. You can instrument your code manually if you want to have more information about that. The Windows SDK has quite some information on how to emit ETW events, and we have a separate session on that on Thursday. And so based on that knowledge, you actually need to start asking, why am I loading all of those modules? We had some other low-hanging fruit actually in this particular project, like loading something like Microsoft.json, which was a helper function library that we actually wrote. Well, we could maybe just merge a couple of things inside our existing project if you are only using a little amount of types from those particular assemblies. Beware of inlining, as you saw, like the method impl options is one way to sort of suppress that kind of thing. And finally, something we are not going to talk about in the cold start part, but we'll actually come back to that later a little bit, is Ngen. So Ngen allows you to optimize images by actually sort of pre-jitting them at install time. Now, it's an interesting trade-off to be made there, because Ngen typically helps for a warm start because you don't have to JIT compile functions at the point you actually load them the first time. But on the other hand, the binary image size tends to be bigger for Ngen images, making the I/O time in the cold start case bigger. So actually, it's a trade-off there, whether you actually want to optimize the warm start performance or the cold start performance. So that's also something to keep in mind. And maybe you don't have the option to Ngen your images because you're not using particular installer technologies that can actually do that for your application. So again, the key to success here is to measure things instead of just blindly trying to do certain things. Okay, so next thing is warm start. When we start our application, it seems to take a while to get to the initial loading screen and to the initial page where all my contacts are.
So here's another Xperf profile, just like we saw before, except you notice this time the CPU is very busy the entire time. Here we have a CPU sampling by process. This machine is dual core, so you see at this initial startup time, we're using 100% of that first core. I can quickly overlay the fishbowl events themselves on top of the CPU trace, so we can see exactly what the CPU is doing during specific events during our application. So you can see that our main window constructor now takes significantly less time because it's warm. We're not blocked on disk I/O. Now, important things to remember about warm start is that you should expect to see the CPU busy. You should not expect to see as much I/O as cold start. You've already loaded these pages. So in general, it's mostly about CPU time. Here we see a dip in the CPU. Generally, that indicates that we're blocking, either on a network socket or something else. In this case, if we hover over this event, it says that we're navigating to the login page. So we definitely have some network I/O that we can't avoid here. And if you remember what we did at this point, we're still using some CPU. We're showing a progress page. We're indicating to the user the application is still here. We're still live. We're talking to the network. We're not hung or anything like that. And then once we're done with that login, we come back and we actually are using the CPU again. Now, if you have trouble with warm start, really the first tool, after you've identified any blocking and dealt with that, is a CPU profiler. So we'll go ahead and run the application just so we can take a look at what warm start looks like and see what areas we need to address. We showed a splash screen that we have verifying permissions and loading. And now we have a little bit of a hang there, a little bit of a white screen before we actually see the content of our application loaded. Now in this case, this list box is not virtualized. We can verify that using WPF perf. This is part of the Windows Performance Toolkit and part of the Windows Presentation Foundation tools. And so we'll attach this to Fishbowl. And one thing that this does pretty well is show you the element count. In this case, when it comes up, you can see that this main window actually has a lot of elements. We actually have 6,000 elements. This is very heavy, but not necessarily unusual. And most of these, if we drilled down, we'd see are in this scroll bar. In this case, each of these, this is a list box. Virtualization is not turned on. And the reason virtualization is not enabled is because each of the list box items has a variable height. Each news message here has a variable number of I guess these are replies to it. And basically, to use virtualization effectively, the scroll bar wouldn't be able to predict how long the actual list box is without actually doing the layout for all these items. So in order to have an accurate scroll bar, the developer made a conscious choice to sacrifice memory and in some cases possibly warm startup time and to spend more time in layout to have that scroll bar be accurate and enable that scrolling. So what we do, we'll now switch to, we still don't want that white screen experience when we dump all the downloaded content into there. So we'll switch to the CPU profiler. In this case, this is the CPU profiler that comes with Visual Studio Team Suite. And basically, you can start the application, pause and resume the profiler. So basically what I've done is taken a CPU profile of exactly that region of time where we're seeing that white screen. So we switch over to the call tree. We have sorted by inclusive time. So this is basically something you should be familiar with. There's plenty of CPU profilers out there. We can see that we do have a background thread doing some work. But really what we care most about is this main thread 56% of the time. We can use the expand hot path feature to quickly drill down and see where the profiler thinks that most of the time is going. And you see it fairly quickly expanded down to update layout. So we're spending 40% of our CPU time during that white screen updating layout. And that makes sense. We have 6,000 elements to lay out, so it takes quite a bit of time. So in this case, we talked about perceived performance. And what we did here and what the developer did was you have to sometimes think a little bit outside the box. And I'll show you what we did with this. So now we still have the same splash screen, same verifying permissions hitting the network, loading. And now watch the scroll bar over here. What we did is decided not to pay all that layout cost up front. In this case, the first few items were added immediately so you could see. The user immediately sees, we've got the first items in there, layout happens on only a few items, and it's very quick. And then you get sort of a loading experience as a background dispatcher timer fills in the rest of the list. So we're still paying just the same amount of CPU time during layout, but it feels more responsive because the user doesn't have to sit and wait for that first item to be visible.
Yeah, and as soon as we actually publish the sources to Fishbowl, you can actually find the code of that in something called incremental load list box. We've actually implemented this technique where we simply add things, and then on a background dispatcher work item, we actually say add a thing to the list. So that's actually what's happening here. Okay?
So the real takeaways from Warm Start, just use your CPU profiler because it really is almost just like a runtime scenario.
Okay, let's switch over and actually summarize this one very briefly. Oh, I'm actually going in the wrong direction all the time. Excuse me. So important thing is, of course, in this particular case, the CPU. You actually want to see the CPU kind of high, because if it's low, you're actually blocking on the startup path. Of course, if you can actually defer any work that you're doing on the startup path, that's also a good thing to do in general. Secondly, and well, that's actually what I just said, like if you can delay certain work items, and that's actually something we actually saw when we were creating this application. We were doing quite some preloading of stuff, and in the field we've seen things like people loading a massive amount of video codecs all on the startup part just to have them there, and then the application is only using a couple of them. Well, then you've just wasted quite some startup time to be kind of optimistically loading things. And for Warm Start, it's like most things, not an exact science. Perception is key in this particular case. So we did some iterations internally with lots of people who have large contact lists and everything. And they actually said, well, this performance doesn't look like it actually needs to be. So we introduced things like the splash screen, which was actually added in .NET 3.5 SP1. So we're using that one over here as well. We're using some transition effects, and we're also using that incremental loading list box that we've actually introduced here. So typically for Warm Start, the most important thing is to ask your customer, know what your customer wants, and actually take a look at what they actually find about your application when it actually starts up. But there are some kind of problems in the runtime performance of this application, more specifically the photo view. So what's up with that one?
So we have some reports that this photo gallery is not running quite as fast as we'd like. We add a neat effect so that when we resize, the photos will kind of slide into place. but the frame rate, at least on some machines, is fairly low. And you can see it sort of jerk a little bit there as I slide in and out. The best thing to use for diagnosing this sort of information is start again with WPF Perf. Again, this is part of the Windows Performance Toolkit. It will show you on the right-hand side here a graph of roughly where the CPU time is going. It splits it out between layout, rendering, and other large areas of WPF that tend to bottleneck an application. In this case, we're seeing most of the time spent in rendering, so we know that while we're doing that animation, rendering each of those tiles is very expensive for whatever reason. If this was something like layout, we would look at how complex it is and why we're invalidating layout for the whole thing while it's moving around. In this case, layout is almost free, but we're spending time in rendering, so we'll switch over to the perforator tool. Visual Profiler does have a fairly pronounced effect on the application, so make sure you detach it first before selecting the other tool. Perforator is all about rendering performance. It shows you various statistics like the frame rate, how much video memory usage. It has a bunch of diagnostic tools down at the bottom where you can check and uncheck these toolboxes to make your application perform differently and see various things. And it has the number of intermediate render targets per frame. So in this case, we've attached the perforator tool. We kind of scroll around, observing our frame rate. And we switch back. We can see that as I was scrolling, the frame rate dropped a bit. In this case, it dropped down to 30 or so. And what's interesting is that the number of hardware IRTs per frame has shot up to about 20. Now, a hardware IRT is not in and of itself a bad thing. An intermediate render target is what that stands for. And basically, there are some features of WPF where in order to compose the full scene, it needs to use an intermediate rendering. Things that would cause this would be opacity effects, visual brushes is an obvious one, and effects. In this case, what happens is WPF has to render something off-screen to a video memory buffer or a system memory buffer. That's the difference between hardware and software. And a hardware IRT is basically a buffer off-screen in video memory, whereas a software IRT is a buffer off-screen in physical memory. And then that buffer is then used to compose the final scene that is presented to the user. So for the most part...
Yeah, so what makes actually those RFTs kind of expensive? Because I'm just seeing them, okay, we're sending it to the video RAM. I imagine that's kind of an efficient operation, but there is some bottleneck here that drops my frame rate.
It definitely is. It's fairly efficient. There's a fairly high cost per IRT. I mean, you can imagine that not only do you have to copy that video buffer, there's an extra copy to compose it to the final scene, but also there's a fairly heavy context switch cost in the rendering pipeline to switch between render targets just on the video card. Video cards are really designed for high-performance 3D gaming where you wouldn't really have this sort of intermediate render target composing going on. Definitely software IRTs are far more expensive than hardware IRTs. And again, it's not necessarily a bad thing. If you have a few IRTs, but your frame rate is staying up, then that's okay. In this case, so the tools for diagnosing these are not particularly great right now. Like I said, we have things that cause these are just things to look for in your code. So we know we have a lot of IRTs. We need to go and look at effects. We need to go look at opacity masks. We need to go look at visual brushes, things like that. In this case, each of these photos groups has a drop shadow effect applied to it. As I hover over, the depth and the opacity of that shadow is expanded so you can see the effect sort of animate in and out as we go over it. As we looked at the code, and I won't actually go into this in the interest of time, but if you look at the code, what happened is the developer who added this feature added this drop shadow effect, put the effect on each of these tiles so that the effect could be animated. The fix, and I'll show right now, if we run the fixed version, what we did is we actually added a second element to each of these and applied the drop shadow to that element. Then the element itself could be hidden or collapsed so that that effect is doesn't take place in the rendering pipeline. This is potentially an optimization that WPF could do internally. If a drop shadow effect has a 0 depth, just don't render it, but that's not something that's actually done. In this case, if the element is collapsed, then it won't be rendered. So I'll switch back to Perforator, select the fishbowl application, and this is the fixed version. So you can see as I resize, it's a bit snappier. The elements kind of snap into place and do a little landing animation. And the frame rate doesn't drop down to 30, except there. And the number of hardware IRTs per frame is now down to about 11 or 12. So we haven't gotten rid of all of them. There's still possibly some effects or opacity masks in the application. But as long as the frame rate is staying pretty high, those aren't necessarily an issue at all.
So essentially, the problem was that the shadow effect was applied to all the elements, and that was sort of being animated as you move over it, right?
Correct.
Okay. I believe we have a separate sample of that, like in isolation, that we could show.
Sure. So here I'll bring up. Oops. I'll bring up the code here. We have a. Basically, here's the same thing in a XAML here. You can see I have a red rectangle. As I hover over it, a shadow appears and disappears. The rectangle itself is right here. And I'm actually going to have to restart it because I closed Perforator, so give me 1 second. Basically, this is the same sort of thing in a very simple scenario that you saw in the fishbowl application. I have a rectangle with a trigger on mouse enter, a trigger on mouse leave, and a drop shadow effect that is only visible as I move the mouse cursor over it.
And so the effect is actually animating the shadow depth to a non-zero value, right?
Yeah, so I'm effectively animating the shadow itself. And we can see as I resize this, cause it to redraw, even though you don't see the shadow, we have a hardware IRT. The alternative that we used, I'll just comment this out.
I think we need that.
And comment in the better version right above it. And now,
I think we have the comment on. The comment needs to start with lower than bang. Oh, higher up, higher up.
Yeah.
Okay, higher up.
Oh, yeah, there.
Here, yeah. Okay. That should be better. And I think we have some excessive insertion of a page tag there.
Yes, we do.
It's actually not a valid one. Okay.
And now we have a green rectangle, and you'll notice this has exactly the same effect. The drop shadow appears and disappears as I mouse in and out. But Perforator, if I do a resize while the effect is not there, cause it to redraw, no additional IRT is created. Of course, there's still an IRT when the shadow is visible, but not when it's invisible. And the way we accomplished this was to actually have two rectangles. So if you can see this here, we have one rectangle at the top with an effect on it, and in this case, the opacity of that rectangle is 0. So that rectangle is effectively hidden and will not participate in rendering. The actual visible rectangle is here, which has the triggers on it, but no effect. So that's just one possible technique to avoid this sort of thing.
And so in this case, the triggers actually make the other rectangle visible.
Yes, exactly. The animation animates the other rectangle to be visible and then animates the shadow.
Okay. So let's switch again and actually get a couple of takeaways from this particular part. So IRTs, I have a couple of them actually sitting here. Effects, clips, opacity mask are places that can actually cause IRTs. Again, use the tools to see whether it actually affects you. More specifically, look at the frame rate. Of course, first ask your users whether they see kind of a lag in certain animations, and you will see it yourself as well. If that's the case, the next thing to look for are potential use of IRTs. Bitmap effects are a notorious source of those. Those were actually present in v3.5 and below, v3.0. We actually got rid of those and replaced by other functionality in the framework. And where we actually could, we optimized things so that, like, Software IRTs do not happen that often anymore. What we haven't talked about in this particular case is element count. The number of elements is also something that can cause certain problems when you're doing input and routing for events and commanding. We actually have some info on this slide in the speaker notes on how to actually think about that. And I actually have a couple of resources sitting further as well. In .NET 4, we also introduced some kind of trade-off mechanism, which is called cached composition. And so what you're doing there is instead of rendering certain things, you can actually sort of cache the render scene in memory. And in that particular case, what happens when the thing needs to be redrawn on the screen, it can actually go to that cache. So the point there is that you're trading off video memory for actually CPU utilization at the point you actually need to render certain things. WPF will, of course, invalidate that particular cache in case the thing, the scene gets invalidated. But so that's something you can actually turn on by a single property on elements. So that's something new in .NET 4.0, which we can't use in this particular case because we're targeting .NET 3.5. So important things here to be aware of is like IRTs, eventing can be a problem in certain cases, but that's not that common. And excessive use of like effects that are sitting everywhere, even if they're not visible, you're actually paying a cost in certain cases. So that's something to see under your tools. Now, there's quite some stuff to be told in terms of runtime performance. So I actually have an additional slide here of things we couldn't actually show. First thing, of course, is don't block on the UI thread. It's amazing how many times that still, happens. We have the technologies, in order to avoid that, using dispatcher and all of that kind of stuff. But don't block on the UI thread. That's an important thing. Secondly, virtualization, which is turned on by default in certain UI controls, is an important thing. Now, we've seen one place where we could actually not use it because we didn't have like homogeneous like items in our particular list box, and we wanted to have that smooth scrolling experience. In that particular case, we turned off the UI virtualization. Now, another thing, of course, is also to use data virtualization, which is something we don't have a silver bullet for. Like, what your data is that you're loading in the application. If you can load it, in pages from a database server or web service, for example, well, you can actually do virtualization, in your data layer as well. So there are a couple of things there to keep in mind. Freeze your freezables is one of my favorite things. That's actually WPF's notion, if you will, about immutability. So if you say that something will not change in the future and you freeze it, well, we don't have to hook up notification callbacks, which can also contribute to certain performance issues if you have lots of things that are freezable but are not frozen. And finally, that's a whole session on itself, hardware versus software. You can use WPF in a variety of places, including high-end machines and low-end machines, but also over RDP and virtual machines, all of that. Now, when we're actually rendering over RDP and virtual machines, we're in a different so-called render tier. And so you can actually find that render capability.tier API inside WPF, which can actually be used to detect in which particular case you are. And then conditionally, you can actually start taking away certain effects, reduce animations, use of 3D, all of that kind of stuff. So hardware versus software is something that, again, depends on the scenario that you're in. If you're actually creating a CAD application that needs to be used over an RDP connection, well, you might actually seriously want to consider to check for the render tier and basically do conditional actions upon that. So lessons learned, I've sort of brought together like all my little things that I have sitting on my monitor at work that I should never do because otherwise those people are like trying to kill me. I shouldn't load that much images and actually make sure that I don't have an excessive amount of elements when actually there are problems with memory or rendering. That's something to look out for. Cold start is all about disk I/O, especially modules that are loaded are always suspect, especially if you see things like Windows forms or drawing or certain things that you don't expect on the startup path. Well, analyze that using tools like Xperf. Use also the Cytec memory profiler to see where things are actually being allocated from or what they are being used for. Warm start, there is all about perceived performance. Have like loading animations, add things incrementally to list boxes, delay work where possible, and of course avoid blocking. You will have to go out to the network in times of cloud computing and whatever, but even if you do so, well, you shouldn't actually keep the user staring at the blank screen while you're doing so. So their perceived performance is kind of a very important thing. And then for runtime, The things we saw actually in the session here were things like IRTs that can be caused by certain effects. In that particular case, you use the WPF performance tools, including Perforator. You can find all of those tools as part of the Windows SDK that comes with an installer for the WPF performance tools. And in there, you will actually find that Perforator tool that's used to see everything that has to do with effects and the rendering pipeline, if you actually will. So while composition is still power, I think we need to add one little thing here to the overall equation, and that's measurement. We see lots of people, shooting themselves in the foot by letting things derail a little bit too much without doing proper measurements and actually seeing what the real scenarios are of the application and identifying the things to focus on, like the perceived performance when it loads, startup time, certain effects that are kind of excessive, but you want to have them. Actually, it's better to sort of catch them early, especially when you have like designer-developer collaboration and you get like a huge update to your XAML back. Well, at that point, it's a good time to sort of just take a look in certain tools that you don't see unexpected things happening there. So measurement should be sort of in the center, and I hope, well, that's kind of cheesy, that we can now have peace between those two parties, although there is no real war going on. I have some resources here with the tools that we've used, so you can find all the tools online. For memory profilers, we've used the Cytec.net memory profiler, which is not free, but you can actually get other tools or actually pay this one. It's really a very good one. We have some performance blogs on .NET in general, which is Rico Mariani's blog, and we have a WPF-specific one from Joseph Goldberg, who is the WPF performance PM. And at the top of this thing, we also have the Windows SDK performance tools, which I assume that everyone has installed with the Windows 7 and 2008 R2 SDK today. OK, with that, I want to open up for questions. Stay in touch and actually come and see us also at Ask the Experts tonight, and we'll also be having shifts on the booth. So if you have any question whatsoever, come to us, talk to us, or send us email. Thank you.